Hello everyone, how are you? I hope that you are fine and in the best of your health at your respective places. Myself, Dr. Mahindra Guleria, and I am here with my third video. And in this video, I am going to discuss with you limitations of chemical thermodynamics. So before coming on to the topic, I want to say that if you have not subscribed my channel, so please subscribe it and also press the bell icon. So let us start the discussion on the topic. So in my previous video, I told you that thermodynamics have applications in almost all branches of science. It has application in physics, chemistry and also in engineering. But at the same time, it also suffers from certain limitations. So today I am going to take up these limitations. So let us discuss limitations one by one. So the first limitation is that it deals with macroscopic properties of the system arising due to bulk behavior and not with microscopic properties. So in order to explain or in order to understand this limitation, we have to understand the two basic terms first. Number one is what are microscopic properties and what are macroscopic properties. So let us understand with an example. So I have taken a gas enclosed inside a container, and this gas is composed of very small particles, and these particles could be atoms or it could be molecules. If we have a noble gas, we know that noble gases exist in atomic form like helium, neon, xenon, or we can also have gases like nitrogen, oxygen, which exist in molecular form. So all these particles, they have different individual properties. For example, each particle will have different position, different velocity, different momentum and different energy. So when we study the properties of individual atoms, molecules, or I can say particles, then those properties are called as microscopic properties. So we can say that properties of these small microscopic particles are called as microscopic properties. What in chemical thermodynamics, we don't deal with it. To study these properties, we have another branch of thermodynamics which is called as statistical thermodynamics. So at present we are studying classical thermodynamics, not statistical. So classical thermodynamics deals with the macroscopic properties. So let us understand that what do we mean by macroscopic properties. So if we want to measure the pressure of this gas, then what we will do? We will measure the pressure of entire gas, not the pressure of a single molecule. Okay, so that pressure is due to all molecules or all atoms, and so the pressure is the property which is arising due to the group like behavior of these particles, collective behavior of these particles. We are considering the gas as a single entity. Understanding? So pressure is a macroscopic property because it arises due to the collective or the bulk behavior of matter or bulk behavior of these particles. Now you might have understood what is bulk behavior, collective behavior together. Likewise, when we measure the temperature of this gas, we measure temperature of entire gas. We don't measure the temperature of individual atoms or molecule. So temperature is again a macroscopic properties. When we measure volume, then again we measure volume of the entire gas. Understanding? So volume is also a macroscopic properties. So properties which are studied for a group of particles and arises due to their collective behavior or bulk behavior are called as macroscopic properties. So we can say that chemical thermodynamics will not help us in understanding the structure of matter, because matter is composed of small particles like atoms, molecules, ions, and if we want to study the internal structure of matter, then we have to understand the properties of atoms, molecules or ions. But as I said, the chemical thermodynamics does not deal with it. No doubt, we have studied the atomic structure also, structure of atom, all that, the structure of matter has been studied. But this cannot be done with the help of chemical thermodynamics because it deals with only macroscopic properties. So this is the first limitation which I have discussed with you. Now let us discuss the second limitation of chemical thermodynamics. That it does not tell us anything about the time taken by the process to complete or the rate of the reaction. In my previous video, I told you that chemical thermodynamics is very helpful in explaining the feasibility of a chemical process, that whether a chemical process would occur or not. But it does not tell us anything about the time taken by that process for its completion, that when this process will complete. Or in other words, I can say that it does not tell us anything about the rate of the chemical reaction. Now let us understand what is the rate of the reaction. By considering a simple reaction, that is, we have A changing into B. Okay. So initially when time is t is equal to 0, a reaction has not started, we have only A. And when the reaction starts, the concentration of A is decreasing. And suppose after time delta t seconds, the decrease in concentration of A is delta A. Okay, then what is the decrease in the concentration of A in 1 second? In 1 second, the decrease in the concentration will be equal to delta A upon delta T. So this is the rate of reaction, that is decrease in the concentration of reactant per second. How much reactants are being consumed in 1 second. We can also express the rate of a chemical reaction in terms of products, because the concentration of product is increasing. So if in delta t second, increase in concentration is delta B, then in 1 second, what is the increase in concentration of product? Delta B upon delta T in 1 second. Okay. But here we put what, plus sign, and here we put minus sign, which indicates that concentration of the reactant is decreasing and concentration of the products is increasing. And the unit of this will be concentration, it is expressed in moles per liter, and time in second, and the unit will be moles per liter per second. So I have given you a small idea about the rate of a chemical reaction. But we know that we have a separate branch of chemistry, chemical kinetics, which deals with the rate of the reaction, factors affecting the rate of reaction, and everything about the rate of a chemical reaction. So this is the limitation, second limitation of chemical thermodynamics, that it does not tell us anything about the rate of a chemical reaction. Our third limitation is that it is concerned with initial and final state of the system, and not with the path by which the change is brought about. Again, to understand this limitation, we have to understand what are the state functions and what are the properties which depends upon the initial and the final states. Let us take example that I am standing here. I am standing at this particular position. At this position, I will be having certain amount of potential energy. Now, I move up, that I go on the top of the roof of my house. Now I am at this position. Initially I was here, and now I am at this position. And I have gone up to the height h, suppose. Okay. Now, what would be my potential energy at this point? It would be equal to mgh. It will be equal to mgh. So, at this point, my potential energy is mgh. Doesn't matter that how I have reached at this place, because I can go here through stairs or I can go here through a lift. I can directly go here through a lift or I can opt stairs also. This means that there are two paths by which I can go here, but doesn't matter that which path I have followed, my potential energy is going to be mgh. So what I want to say, that potential energy, it is related with the initial and the final state of the system. It has nothing to do with the path. Okay, so chemical thermodynamics deals with the properties which deals with initial and the final states, and it has nothing to do with the properties which do not deal with initial and final state. So these are called state functions. I want to explain it further with the help of another example. Volume is also a state function. That is, let us consider a pressure volume diagram. Let us consider a pressure volume diagram. So on this axis pressure is increasing and along this volume. Okay. So when pressure is very high, volume will have less value, will be having less value. So I think when pressure is this, the value of volume is this. When pressure is very low, value of the volume will be very high. Understanding? Because both are inversely proportional. Boyle's law. So these are 2 points. This is the first point and this is the second point. Okay. Now I can go from this point to this point by following this path, or I can reach here following this path. Okay. What doesn't mean? It doesn't matter that which path I have followed, the final value of the volume is going to be this, and initial volume is going to be this. And what would be the change in volume? If I consider volume is V2 here and volume is V1 here, that the change in volume will be equal to V2 minus V1. Have you understood? So this means that volume is a state function. It depends upon the initial and the final state of the system. It does not depend upon the path followed. Internal energy, enthalpy, free energy, entropy, all these thermodynamic functions are state functions. So here when I am discussing this, I want to discuss what are the path functions also. So path functions are those functions which depend upon path. For example, work. When we do work, then naturally if I am going from this path, I am following this path, that this point is A and this point is B. If I am going from A to B following this path, then the work done will be different. And if I follow this path, work done will be different. And you might have seen, if you travel through a longer path to go anywhere, then you have to do more work. And if you opt for a shortcut, then you have to do less work. This means that work is a path function. It does not depend upon the initial and the final state. Likewise, heat is also a path function. For example, we have fire here. आग जलाई हुई है यहाँ पर. Okay, and when I am very near to the fire, I am going to get more heat. As I move farther from the fire, I am going to get the less heat. This means that heat is also a path functions. So path functions we study in thermodynamics by expressing them in terms of state functions. Heat and work will be expressed in terms of state functions, and only then they will be calculated. So now I hope that you might have understood what are state functions and what are the path functions. So chemical thermodynamics, it deals with only state functions and not with the path functions. Now this limitation can be interpreted in another manner. when the thermodynamics does not deal with the path, then it would not tell us anything about the mechanism of the process. What is path? Path is the mechanism of the process. How that process is being carried out. I am going through the stairs, it is one mechanism, and I am going here through lift, another mechanism. And you know that in chemistry we study mechanism. Let us apply this concept to a chemical reaction. That is, I have a reaction, that is A changes to C. Then thermodynamics will deal with what? Initial and the final state. It will deal with only A and B. Understanding? But the mechanism of the reaction, the path of the reaction could be different. A can go to B first, in the first step, and in the second step B will go to the C. This is the mechanism. And then we write the overall reaction, we cancel B with B, and then A is changing to C. This is our overall reaction. So in chemistry, a due consideration is given to the mechanism, the path by which the reaction takes place. But the chemical thermodynamics, it has nothing to do with the path. It considers only the initial and the final state. So I can say that chemical thermodynamics does not give us an idea about the mechanism of a chemical reaction. Understood? So next limitation is it gives relationship between various experimentally observed properties, but is unable to give actual values of these properties. Very interesting limitations. That it gives us relationship between various experimentally observed properties. So what are the experimentally observed properties? Pressure is experimentally observed, volume is experimentally observed, temperature, energy, all these properties are experimentally measured. So what thermodynamics do? It derives some very useful relationship between these properties. Okay, and with those relationships are very important. Sometimes my student asks me that, sir, what is the need of deriving these long equations and how do they help us? So I used to tell them, let us consider a very simple equation, that is ideal gas equation, that is PV is equal to nRT. Okay, and if we have an ideal gas, then this equation is going to be of great help for us. If I have measured temperature experimentally, and if I have measured volume experimentally, then I can calculate the pressure with the help of this equation. That is P will be equal to nRT upon V. So I know the number of moles, I know gas constant is there, constant, temperature I have determined experimentally, and volume also. Then this equation can give us an idea about the pressure, that what pressure that gas is going to have. Understanding? So this means that thermodynamics will derive, as we will see in the later part of this chapter, equations will be derived relating these variables. Here also 3 variables are related: pressure, volume and temperature. But the value of pressure given by this equation, we cannot say the value of pressure given by this equation is actual value, because for actual value we have to perform the experiment. This value could be very near to the experiment value, but actual value we have to determine experimentally. So this is the 4th limitation, that it gives the relationship between various experimentally observed properties, but is unable to give actual values of these properties. Actual values mean to say values which are determined experimentally. It can give us an idea. The value could be very near to the actual value also. And another thing which I have not written here is that chemical thermodynamics also don't tell us that how do these properties arise. For example, it talks about pressure, it talks about volume, but it will not tell us that how the pressure arises, because everybody know that if we have a gas inside a container, that from where the pressure will arise, that the pressure will arise due to the bombardment of the walls of the vessel by the molecules or atoms, the particles inside the vessel. Okay, so it talks about the pressure, but it does not tell us about how do that pressure is coming into existence, from where that pressure is coming. So this is also a very serious limitation that the chemical thermodynamics has. So my dear friends, I have discussed in detail, to the best of my knowledge, the various limitations of chemical thermodynamics with you. And if still you are having any doubt, as I have said earlier, you can leave a question in the comment box, or you can also contact me on my WhatsApp group or a Telegram group we have. Okay, I am always there for you. So I hope that you might have enjoyed my today's video, and at last I am again saying that please, if you have not subscribed, please subscribe my channel and also press the bell icon. And in my next video, I am going to cover some very basic terms used in chemical thermodynamics, and which are going to be as very important. Because if we know the basics of subject, then we can study it in a better way. So thank you very much for watching my video.